Okay, good evening. This is Professor David J. De Los Reyes. It's March 18, 2023. The time is 9:35 p.m. Los Angeles time. Okay, my topic for tonight will be a very interesting one. It will be a circuit analysis problem by using Laplace transform. Okay, I have already derived the formulas on how to take the Laplace transform. Okay, so let's proceed with an actual problem with the circuit analysis. Okay, I will check my camera. Oh, it's fine. My topic for tonight will be a circuit analysis problem using the so-called Laplace transform solution. So this is now advanced math, lesson number 22. Okay, and this will be a circuit analysis. This is a series connection of a resistance and inductance. Resistance and inductance energized by a direct current source. So we are asked to solve, meaning the solution using Laplace transform. Meaning our topic for tonight will be, we will try to solve the differential equation by not using the classical solution. It will be by using the so-called Laplace transform. Okay, let's proceed. Oh, this will be the figure, right? RLDC circuit, resistance and inductance connected in series, energized by a direct current source. So after closing the switch, the current circulating will be I. And the problem is asking what will be I as a function of time using Laplace transform. Okay, we will not use the classical solution. So we could check the validity of the answer using the classical solution by using Laplace transform. So guys, what will come out will be the same as the classical final answer. That is, okay, I will read the final answer actually. Current I as a function of time is actually E over R times the quantity 1 minus E raised to minus R over L times time plus quantity. From our classical solution, this is our final answer. And supposedly what comes out is actually the same. Okay, let's try to bring out the Laplace solution. The Laplace solution is the same as from the, no, it's not the same. Initially, we will take the summation of voltages and they should be equal to 0. And any closed circuit, the summation of the voltages will be equal to 0. Meaning, the voltage of the source should be equal to the voltage drop across the resistance plus the voltage drop across the inductance. Okay, let's proceed. So what will come out? It will be plus E minus B sub R minus B sub L, and they should be equal to 0. I will try to place the equation to be look nicer, so I will transpose this negative thing on the right. Okay, so what will come out? E now should be B sub R plus B sub L. Alright? Initially, we started from this. So okay, I will erase this one so it will look nice. Okay, let's try to substitute the value of B sub R and B sub L. E now will be equal to, the voltage across I resistance will be IR, the current passing times its resistance. The voltage across the inductance, whether we like it or not, if it is a coil, okay, there will be a rate of change of current as current passes by through the coil. So actually, the voltage across the inductance is actually the inductance times the rate of change of current with respect to time, or simply di over dt. It's the same from the classical solution. Okay. If we now try to simplify this one, E will be equal to IR. I will repeat it. L times di dt. Oh, this is actually a first order differential equation. If you are using the classical solution, use your knowledge on how to solve a first order differential equation. We have done that already, right? So for tonight, we will be using Laplace transform. So by using Laplace transform, small I as a function of t will be equal to capital letter I as a function of s. The function that is being mentioned under Laplace For tonight, it will now be current. So it should be I of t. That f of t is actually I of t. Okay? So meaning, we are to transform this I of t into capital letter I as a function of s. That is the Laplace transform equivalent. Okay, let's proceed. E is constant, right? So if we try to take the Laplace transform of that, I think that's formula number 2. The Laplace transform of any constant is actually that constant over s. So actually this is, it emanates from E times 1 over s. Right? That's formula number 2 under the formulas that I have derived. So it will be E times 1 over s. Okay? R is constant, right? So if we try to take the Laplace transform of this, it will now be R. This I is now actually, what will this, I of t. So instead of writing I, you just simply put capital letter I as a function of s, right? That function of t is I, so it will be I of s, okay? Plus this function here, L di dt. That's why before we solve this problem tonight, I have shown you the formula on how to take the Laplace transform of any differential thing. If there is a differential thing, we should know how to take the Laplace transform of that. And I think that's formula number 5. Okay, so it will be, L is constant, right? So we bring it out, it should be L. Under formula number 5, it should be S, function of S, but that function is I, so it should be I of S, right? Minus f sub 0 plus. F sub 0 plus is the value of the current at time t equal to 0. You remember that one? So L, the Laplace transform of a derivative will be S times f of s, but that f is actually I, so it should be I as a function of s minus f sub 0 plus. Okay, so we have transformed already the first order differential equation into its Laplace transform equivalent. It's almost as a function of s plus the other constants. Okay, proceeding with the solution. For an RL circuit, f sub 0 plus is actually equal to 0. F sub 0 plus is actually the current at time t equal to 0, and that current is actually 0. If you try to see it from the graph, at time t equal to 0, the current is at the origin, it is 0. So f sub 0 plus at time t equals to 0 for an RL circuit should be 0. So what now comes out? This part of the equation now, sorry for that one. My red pen is almost gone, not yet gone. This is 0. So actually, the f sub 0 plus is actually gone, right? So it will just be simply like this, because there's no value. So from this equation, it now becomes this one. It will be E over S equal to R, I as a function of S, plus L, S, I as a function of S. This is now the Laplace transform equivalent of the first order differential equation. So to solve for capital letter I as a function of S, we will be using algebraic manipulation. Okay? So I place it here, manipulating. Okay? Common factor is I as a function of S. I try to factor out times open quantity or open bracket R plus LS is equal to E over S. I just interchange, right? There's a common factor I as a function of S on the left. I as a function of S times open bracket R plus LS close bracket equal to E over S. Then solving for I as a function of S, we divide both sides by the sum of these, R plus LS. So I as a function of s, capital letter I as a function of s should be e over s, etc. over this one. Okay, r plus L over s. Then, by multiplying both the numerator and denominator by the ratio 1 over L. There's a reason for that, okay? Because if we try to multiply both the numerator and denominator by 1 over L, okay, what will come out? It will be E times 1 will be E, S times L will be SL, and for the bottom portion, R times 1 over L will be R over L, and LS times 1 over L cancels. Right? So what remains is just S. So I as a function of S will be E over SL over the sum of S plus R over L. And if we try to simplify this one, okay, it will be E over SL, okay, we change the operation from division to multiplication. We take the reciprocal of the denominator times 1 over S plus R plus the ratio R over L. And if we try to simplify this one, okay, I will make it as simply E over L, open bracket, times 1 over. I will put S inside, so it will be S times the quantity S plus RL, close bracket. So this is now the resulting Laplace transform in its simplified form after the so-called algebraic manipulation. And to convert this one to its inverse Laplace, we must have to simplify this one as a partial fraction. So I place it here using partial fraction. For the meantime, forget E over L, okay? Just take the equivalent of 1 over S times the quantity S plus RL in terms of partial fraction. So I will place it here 1 over S times the quantity S plus RL should be equal to S is actually S minus 0. Right? It's a linear factor. And S plus RL is also a linear factor. So they are both linear factors, right? So if we try to take the equivalent of this, it should be a constant A over S plus another constant B. They are unknowns for the meantime. B over S plus R over L. And by simplifying this one, okay, what you call this addition of fractions, Mr. Vinci, the butterfly method, right? We cross multiply this one. It is this. Then we cross multiply this one. That's why it looks butterfly, guys. BS. And the common denominator will be the product of S times the quantity S plus RL. Okay, for both the left and right, so they will try to cancel out. Right? So what will remain on the left will be 1 equal to. If we try to expand this one, 1 will be equal to ES plus A times the ratio R over L plus BS. So this is now actually the resulting, they call this linear equation involving the unknown constants A and B. And to compute for the unknown constant A and B, that's why I told you guys, the prerequisite of advanced mathematics is algebra. One of the prerequisites is algebra. Okay? So equating coefficient of like terms, we will start with a term S to the first power. For the left hand side, the S to the first power is nothing, right? So it will be 0. For the right hand side, there is a coefficient A. This is A. And there is a coefficient B. So this is plus B. And this should be equal to 0 because there is no S on the left. So actually A is equal to negative B or B is equal to negative A. We call it equation number 1. This is the algebra portion. That's why I told you we needed an algebraic manipulation. Right? We equate the coefficient of all the terms containing S to the 0. S to the 0 is actually pure constant. Meaning, the constant on the left should be equal to the constant on the right. On the left, the value is what? We got 1. And on the right, R is constant, L is constant, So there's no s, right? And the coefficient, this a here is the unknown a. So this is equal to a times r over l. And we could compute for a, we take the reciprocal of this, a now will be l over r. It should be the reverse of this. Because we will divide this one by r over l. We will divide this by r over l. Okay, so a now will be l over r. Right? We take the reciprocal if we could try to compute for a. Therefore, b will be the negative equivalent. Because a is equal to negative b or b is equal to negative a. Okay? Okay? Therefore, b now should be, take this value a, you place in negative side. So actually b is actually negative l over r. Okay? Oh, that's just pure algebra. So going back to this I of s, capital I as a function of s, I as a function of s should be equal to, I am following this, e over l, okay, times, we now know the equivalent of this in terms of partial fraction. This should be a over s plus b over s plus r over l. It's just a matter of substitution. So it will now be equal to e over l. There is a common factor l over r. We bring it out. Okay? So it will be e over l times l over r times the quantity. What remains inside, we bring out l over r, so what remains on the first one, on the numerator will be 1. On the denominator it says minus. Okay? I retain the minus over here. A plus in a minus will be a minus, right? So this is 1. I bring out l over r. But I maintain the negative sign inside. So it will be minus 1 over s plus r over l. And if we try to simplify this one, this l here cancel with this. So what remains as a coefficient of this, what you call this quantity, it will just be simply the ratio e over r times, open bracket, 1 over s minus 1 over s plus rl. And this is actually capital letter I as a function of s. And to compute for I as a function of time now, okay, we shall go back to the table I have given you guys. So taking the inverse Laplace transform of both sides, the inverse Laplace transform of I as a function of s is actually I, and they should be equal to e over r is pure constant, so we don't touch as 1. We just take the inverse Laplace transform of this. 1 over s is actually 1. Right? This 1 over s, okay, if you try to look back on your table, the equivalent is actually 1. So we replace this 1 over s by 1. And 1 over s plus r over l, this is synonymous to the term 1 over s minus is a. And that is actually e raised to at. If this is minus, this is plus. Okay? But if this is plus, this should become minus. So I place it here. The inverse Laplace transform of 1 over s plus a is actually e raised to minus at. And the value a is actually r over l. So what will come out for the second part, this portion here, it will be e raised to minus r over l. It should be negative, right? Because this is plus. The value of a is actually r over l, so this should be negative r over l times time, closed quantity. So this is now actually our final answer. Okay? That's it, guys. I will try to erase this one so it will look nice. Okay. That's it. After taking the symbol L, what do you call this? Sorry for this one. Oh, my pen was overexposed, so it doesn't write. This is Laplace transform, right? But if there is a minus 1 over here, this should be inverse Laplace transform. Inverse. So I place it here. The inverse Laplace transform of 1 over s minus a is actually e raised to at. And the inverse Laplace transform of 1 over s plus a is actually e raised to negative at. And the inverse Laplace transform of capital letter I as a function of s is just simply I, the 1 we are solving, and the inverse Laplace transform of 1 is just actually 1 over s. So after the replacement of 1 over s by 1, and the replacement of 1 over s plus RL by e raised to negative RL over time, this will now be our final answer. And the graph of the equation will be this, the abscissa is current, the ordinate, the abscissa is time, the ordinate is current, this is a horizontal asymptote, and the value is actually I is equal to E over R, and this is graph of the current. It goes like this. At time t equal to infinity, the current is almost equivalent to E over R. Because at time t equal to infinity, this will vanish. Right? So the current at time t for a long time already, it will just be simply the ratio E over R. It is this. Okay? But initially, it comes from 0, then it rises up, approaching the value E over R. This is minus E raised to minus R over L times time. Okay, that's it, guys. We solved an RL circuit by using Laplace transform, and supposed to be the final answer will be the same as the classical solution. I will repeat it before we will go to tonight. The current I as a function of time by using Laplace will be E over R times the quantity 1 minus E raised to minus R over L times time, closed quantity. And the graph is this. Okay, so for those who are taking up what they call this advanced mathematics, this is for you guys. If you want to subscribe to my channel is at youtube.com/@ProfDavidJ. And if you want to share it, please click share. Good evening from Los Angeles.